Hello, everybody. Mr. Sanford here. Today is Tuesday, April something. 7th? Who even knows? Either way, let's learn a little bit about the greenhouse effect, greenhouse gases, and how they influence the temperature here on planet Earth. All right, before we talk about the anthropogenic or human influence greenhouse effect, let's first talk about the natural greenhouse effect. That is the effect that occurs from greenhouse gases that have no influence at all from human beings. So, if we look at the sun, we have incoming solar radiation, which is shortwave. So, all of the light that comes from the sun, all of the radiation can be described in wavelength. And the shortwave radiation, things like ultraviolet, if we go further shortwave, that's things like X ray and gamma ray. That comes through, that's able to penetrate through the atmosphere, but it's this long wave or outgoing radiation that's coming from planet Earth and would otherwise leave our planet and just radiate out into space, that's able to be trapped by greenhouse gases in the atmosphere. Those greenhouse gases, I'll talk about shortly as to their exact character and what the main greenhouse gases are that are able to trap this outgoing long wave radiation. So, the natural greenhouse effect is really important for our planet because without it, we would be on average, we would have on average a temperature of around negative 18 degrees Celsius, far too cold for liquid water. And as we know, liquid water is key if you want things to be alive, which I do. So, yeah, with that greenhouse effect, the natural greenhouse effect, we get a temperature on average that's more than 30 degrees warmer than it would otherwise be if they did not exist. So what are they? What are these main greenhouse gases? Anyone? Well, I'm staring out into my kitchen, so why don't I just tell you? All right. First up, we have water vapor. Now that may be surprising since most of us know that carbon dioxide is the greenhouse gas that we're most concerned with. But water vapor accounts for anywhere between 36 to 72% of the total greenhouse effect, that is the warming from those greenhouse gases. So when you see those numbers in parentheses, that's its contribution to the overall greenhouse effect, which is again that warming caused by those greenhouse gases. So water vapor is actually the largest contributor to the greenhouse effect. Next, we do have carbon dioxide, which we're familiar with. We'll talk about how much should naturally be there and how much is currently there from human influence, in particular burning of fossil fuels. Then we have methane, which contributes somewhat less than 10%. That's my bread maker going off. Wonder how long that will last. All right. Ozone. That's the stuff that's in the ozone layer. At ground level, it is toxic, but that is also a minor contributor to the overall greenhouse effect, as well as some other minor contributors in nitrous oxides and CFCs or chlorofluorocarbons. And we'll talk about sources of each of these in just a second. All right, so let's start with water vapor. Even though water vapor is the largest contributor to the greenhouse effect, it's not one that we're particularly concerned with in terms of human influence on that greenhouse effect. The reason being is that it's naturally occurring in the atmosphere, but also, as we know with the water cycle, it can't really be influenced to a great degree by humans, maybe on a very, very small scale, but not on a global scale. So, water that's in the oceans and lakes and rivers, even in the soil, surface or subsurface, that water will make its way to the lowest point, and some of that water will evaporate. As it rises, it cools, it condenses and falls back to Earth as either rain, if it's warm enough, or snow, if it's a little colder, and the cycle goes on and on and on. So even though it's the largest contributor, it's not one that humans have a great deal of influence on, although later on you'll see with some positive feedback effects, it can indeed be a larger contributor or exacerbate problems that are originally influenced by other greenhouse gases like methane and carbon dioxide. All right, CO2. CO2 is naturally, so if we were to be looking at this and listening to me speak virtually, a couple hundred years ago before the Industrial Revolution, we would see that carbon dioxide naturally makes up only around 0.03% of the Earth's atmosphere. That doesn't sound like much, though it has increased and it's now up to greater than 0.04%. And that's, of course, due to the burning of fossil fuels, the combustion of fossil fuels, coal, oil, natural gas, and the subsequent release of carbon dioxide into the atmosphere. Now, 0.04% sounds like a very small fraction of the overall makeup of the atmosphere, and it is. But don't be confused about small and unimportant. Though it is small, that increase from 0.03 to greater than 0.04 is causing a lot of forcing on the temperature to increase to levels that will, again, eventually produce positive feedbacks that will be extraordinarily damaging to ecosystems and to us as well. If you take a look, here's a graph that shows carbon dioxide levels in the atmosphere in parts per million, dating back to almost 400,000 years ago up to present. And what's obvious is the trajectory we're now on, that steep slope that you see from 1950 up until today, is completely because of us and the increased combustion of fossil fuels. Now, if you wonder how do we get that information, where do we get that data from stretching back 400,000 years, because obviously we weren't around then, it's from proxy records. Proxies are indirect measurements of temperature, things like ice cores, not quite as far back, but tree rings, lake sediments. We can get this information and use instrumental records. So we can use the records that we have now to test whether we can precisely and accurately predict temperature based on those tree rings, based on those ice cores. And it turns out we can. We can do a pretty good job. And you can see the natural fluctuation. I've talked before about understanding the system, about how we need to understand what the natural variability in that system is so that we can understand when we're outside of that variability and there should be concern. Well, if you take a look at the end, I'm concerned. Methane. Methane is, for the most part, the increase in methane anyway is anthropogenic in that human influence is as a result of agriculture. In particular, ruminants like cows that are able, they have many stomachs and they're able to digest things that we can't, like certain grasses. They have bacteria in their gut called methanogens, and they are able to process some of that food that we can't, but the byproduct is methane. And that methane, if you look at it per volume, is actually has greater temperature forcing ability than carbon dioxide. So if you like milliliter for milliliter, methane is actually a stronger greenhouse gas than carbon dioxide. We also have natural sources that include wetlands. One of those positive feedbacks occurs when we have what were frozen wetlands, where the bacteria in those wetlands are dormant, not active when they're frozen. When they become unfrozen, when they thaw out, those bacteria become activated and start producing methane. And of course, that warms the temperature, which in turn melts more of that permafrost, melts more of those frozen wetlands, which again releases more of that methane. That positive feedback, that cycle continues. Nitrous oxides are mainly from fertilizers, artificial fertilizers, and automobiles. Very small amounts are naturally occurring, but the increase that we see in nitrous oxide is mostly from, once again, human influences. Chlorofluorocarbons, CFCs. So CFCs are mainly from aerosol sprays and were in refrigerants that we Freon that you would use in air conditioners, freezers, things like that. One of the great success stories, environmentally speaking, was the Montreal Protocol in 1987, where the world got together and realized the damaging effects that CFCs were having on the ozone layer. And that ozone layer is important for filtering out some of the ultraviolet radiation, which damages our skin, causes mutation, leads to things like skin cancer. So the world got together and said, why don't we do something to ban these harmful emissions that come from refrigerants and aerosol spray cans? So they looked around and figured out that there was indeed a way to produce aerosol sprays. There was indeed a way to produce refrigerants that didn't involve the emissions of CFCs. So we all just agreed and said, well, if we can do it without it, why don't we? And we did. So it makes you wonder why we can't do that with some other issues that we'll talk about later. But perhaps we will, now that we see that government action, collective action, can indeed work pretty quickly if we're all in agreement. All right, a little note on weather versus climate. This is, grade 9 geography class once again, but it's a mistake we see people that even politicians, leaders, we see they make this mistake every now and then, the difference between weather and climate. I like this quote from Mark Twain. Mark Twain said that climate is what we expect, weather is what we get. And here's what he meant. Oh, nope, better go back. So weather is the short-term patterns that occur in the atmosphere, including short-term fluctuations in things like temperature and humidity and wind, and they're fairly unpredictable. It's very difficult to predict the weather. So, we should give meteorologists a break when you see them on the weather network and they say it might rain, but it doesn't. It's very hard to predict both in space and in time when those conditions in the atmosphere will change in the short term. In the long term, climate, which is that long-term average of the conditions in the atmosphere, long-term averages in terms of temperature, long-term averages in terms of things like humidity, precipitation, etc. It's quite easy to predict the climate. In Canada, for example, the summer in London, Ontario is going to be hot, humid. The spring that we're now entering is going to be rainy. It'll be cold some nights, it'll be warm some other days. The winter, well, that'll be cold. We'll have snow. It's pretty easy to predict the climate. Hard to predict those short-term variations, which are indeed the weather. Now, when we talk about climate change and global warming, again, this is terminology that is often confused, and terminology does matter. So when we're looking at climate change, we're looking at more than just temperature. We're looking at variations in things like precipitation. We're looking at variations in things like wind, humidity, extreme events like hurricanes. Whereas when we're talking about global warming, we're specifically talking about that increase in temperature that is largely due to the increased greenhouse gas emissions that are put into the atmosphere from the burning of fossil fuels. If we look at the evidence, which we always should, there are a lot of different sources which tell us all pretty much the same story. So I'm going to go through a few of these pieces of evidence for climate change and in particular for global warming. So if we look first at the instrumental record, this is the record that we have from weather stations around the world. It starts in maybe around the 1850s, and you can see that there is a fair bit of fluctuation that occurs. Those fluctuations are due to a number of factors. They can be obviously inputs from the sun. It can be changes in the oceans, which leads to oscillations like you have El Nino and La Nina. These things go up and down, but the overall trends since around the 1950s are clear. And you can see the slope of that line if you go from about 1950 up till present. And this graph only goes up to about, maybe 2010. The slope has even increased a little bit more since then. It's clear that global average temperatures are on the rise. That information is also backed up by what we see happening with glaciers. So glaciers are large masses of ice, either alpine glaciers, which exist in mountainous regions. We also still have some glaciers on places like Greenland, but we can see the evidence from certain glaciers. If you look at the two pictures on your screen right now, that is the same glacier at the same location, the same time of year, taken from the same angle. And you can see the extent of the ice back in the 1940s. And then if you look at where that ice now starts in the 2000s, there has been substantial melt. So that glacier has retreated significantly because glaciers will grow. If you get more accumulation in the winter, then you get melting in the summer. They'll retreat. If you get more melting in the summer, then you get accumulation in the winter. And over that 70-year period or so, there has been significant retreat of those glaciers. Sea level rise. We know that the sea has been rising, and of course, that is a threat to coastal communities all over the world. Island nations are in particular trouble with that sea level rise. Sea level rises for a couple of different reasons. So you can have some sea level rise because you get melting of ice that was on land, and that water, of course, makes its way to the lowest point, which is indeed the ocean. But you also get a more significant factor in that sea level rise is the increase in the temperature of the water itself. So when you increase the temperature, those molecules of water, they will start to move faster and further apart. So when your temperatures are colder, the water itself, those molecules are closer together, not moving as fast. You increase the energy in them, increase the temperature of those molecules. Now they're moving faster and further apart, and that added space is now shown in a sea level rise. So when you get a combination of that ice that melts from land and makes its way to water, that will cause a rise. But you also have ice that was on water, ice that was on the oceans, which is pushing the ocean down. And obviously, like you in a bathtub, causes the water to rise. When you get out of the bathtub, it causes that water level to go back down. So when the ice melts, it actually, that force that's pushing the water is gone. However, it's counteracted by that increase in the volume caused by the increase in the temperature of the water, making those molecules move faster and further apart. And overall, the net is an increase in that sea level, which again is a great threat to coastal areas and also in particular island nations. We can also look at that Arctic sea ice. And if you take a look at the picture there, that yellow line is the extent of the ice in the late 1970s. And you can see this picture, I believe, is a satellite image taken sometime in the early 2000s or mid 2000s. You can see how much melting has occurred. And that melting, again, is a direct result of the increased average temperatures we have seen around the globe. When we're looking back before we had an instrumental record, it's important that we're able to find ways to figure out what the temperature and what other climatic conditions were like, dating back thousands, even hundreds of thousands of years, again, so we can understand the natural variability of the system. And we've got many ways to do that. So there's an entire branch of science, paleoclimatology, that seeks to understand what climates were like before instrumental records existed. And they use things that are called proxies. And those are things like tree rings, like ice cores, like lake sediments, or things called varves, in order to figure out what certain climatic characteristics, temperature, precipitation, even ice cover, including the certain gas content of the atmosphere at certain times in the past. They can figure that out using some of these proxies. Tree rings. So, let me go back again. Tree rings are pretty straightforward. In areas where you have variability in seasons, you get distinct rings occurring in the trees that represent the growth of that tree growing during the growing season. The trees are largely dormant in the winter in areas like we are, but right about now they start picking up. And if you take a look at the picture there, those larger rings those are years when the temperature was warmer, when precipitation was greater. So the soil moisture content was better in allowing the tree to grow larger, to grow more during those years. So what scientists will do, in this case, they're called dendrochronologists, is they will take a look and they will be able to figure out from the size of those annual rings what the average temperature was, what the precipitation was during those years, dating all the way back. In this case, I don't know, someone else maybe can count all those rings. This tree might be 50 plus years old, but we have trees that can live for hundreds or in some rare cases, thousands of years. And we're able to take the information from the last, say, 50 or 100 years, compare those ring sizes to actual data that we have for things like precipitation, for things like temperature, and we can develop a model that we can then use to go all the way back to the very beginning of whenever that tree started growing, and we can figure out what the conditions were like then that caused those rings before we had an instrumental record. Ice cores, you can see here that what occurs similar in a way to the tree rings is you get a layering effect. And that's from even in places up north where, in the Arctic, it does get above zero at times in the summer. And certainly you get heavy accumulation of snow and ice in the winter. And what that does is new layers of snow and ice will compress and compact previous layers. They will subside a little bit, melt a little in the summer. Then the next winter, again, you get layers of ice, snow and ice that, again, compact the layers below. And it forms these kind of rings almost like you see on the trees. And you can tell by the thickness of those, again, what the temperatures were like. And you can get an idea sometimes about precipitation depending on where those ice cores were taken from. One you might not have heard of before are things called vars. And these are sediment layers that are laid down often in glacial lakes. So what occurs is, again, in the winter, you get accumulation of that snow and ice. In the summer, you get melting. And if you look at alpine glaciers and lakes that are in alpine glaciers, what happens is in the winter, that ice piles up, the glacier advances further down the mountains. In the summer, when that glacier starts to melt, with it, it takes sediment and it distributes that sediment to the low points, which are these lakes. And the sediment builds up, and of course, the weight of the water above will compact that sediment. So you get this seasonal effect where in the spring and summer, you get melt of that, and that glacial meltwater will take with it all the debris, all that sediment that exists on the side of the mountain. It will settle into the lake. And then in the winter, of course, you won't get any of that sediment. So it sits there, it's compacted and compressed by the weight of the water above. In the summer, of course, once again, you get new melt, new sediment being taken down with that melt water. And again, it will settle out into the lake, form a new layer. So you can tell by the size of that layer, a larger layer indicates that you had a warmer year because you had greater melt. With it, that melt water takes a lot of sediment, and that sediment again will settle to the bottom of the lake, be compressed by the water above, and that's how you get that layering effect. So there are arguments you might hear that, especially if you look at the variability that exists in the temperature record, and even if we go back using our proxies even further, that, hey, it was warm well before human beings even existed, much less started to industrialize and burn fossil fuels on a mass scale. And that's true. That's 100% correct. It certainly was warmer in the past and would continue to fluctuate if human beings were not here. However, don't confuse the issue. Just because it was warmer in the past because of a certain reason, like perhaps volcanism, so volcanoes going off, or perhaps something to do with the orbit of our planet and the wobble compared to what it is now. It doesn't mean that the current increase in temperature that we see right now is for that same reason. And in fact, we know that it's not. So the warming that we see now, though it has occurred in the past isn't due to any of those factors that it was in the past before human beings. It's directly attributable to the burning of fossil fuels caused by us. Uh, Also unseen in the historic record is the rate at which the temperature is increasing. It is increasing at a pace that is alarming right now. One of the big problems being that the environment can't adapt when things change so quickly. So there are possibilities for more mass extinction events when you don't allow time for adaptations to take hold. That being said, I'll let you click on this when you have a second. You can click on that link, and that will show you some of the past fluctuations in temperature, what caused those, and why those are not the cause of the current increase in temperature that we see today. Oh, why, I think we're at the end. Well, I hope you enjoyed this. I think I did an okay job. Um, yeah, we'll try this again another time, and I hope everyone stays safe. Wash your hands.